Hello, and welcome to the lecture on Chapter 24 on the topic of magnetism. This is our third chapter in our discussion of electromagnetism, and the first time we've talked about magnetism. The last two chapters, we introduced electricity both at rest and in motion. And here we are talking about the other side of the coin, magnetism, and we'll bring it all together pretty soon. But what is magnetism? What are magnets? Well, you probably have some idea, but let's talk about where it comes from. All right? So we're going to talk about magnetic forces, magnetic poles, magnetic fields, magnetic domains, right? Lots of key terms are getting out of the way. Electric currents and magnetic fields. Okay, so that's going to be one of the important ideas that's going to unite electricity and magnetism. Electromagnets, how you can create a magnet with an electric field. And magnetic force on moving charged particles. All right, so that means that not only do electric currents create magnetic fields, but also magnetic fields affect currents, which is moving charges, and magnetic forces on current carrying wires, which is a particular kind of subcategory of the one above. And in order to kind of focus on the main story here, I've decided to leave off Earth's magnetic field and biomagnetism and not cover those topics. All right? So, magnetism, what does it mean? Well, the term magnetism comes from the name Magnesia, a coastal district of ancient Thessaly, Greece. And that's because that's where the naturally magnetic stones were discovered. So unusual stones were found by the Greeks more than 2,000 years ago. And these stones, called lodestones, right, and that's popular kind of in the mythology of alchemy, right, the idea of the lodestone, had the intriguing property of attracting pieces of iron. Magnets were first fashioned into compasses and used for navigation by the Chinese in the 12th century. Okay? So, kind of fascinating history of people being, of course, very curious about this phenomenon of magnets and magnetic forces just kind of seeming to exist naturally in certain rocks. All right, so the force between any two charged particles depends on the magnitude of the charge on each and their distance of separation is specified by Coulomb's law. Okay, we saw that 2 chapters ago. But Coulomb's law is not the whole story. That's why we're talking about magnetic forces, because only then can we really understand the whole idea about electromagnetic forces, because it's all connected, okay? Totally separate from gravity, but electromagnetics are united. So when the charged particles are moving with respect to each other, the electrical force between electrically charged particles depends also, in a complicated way, on their motion. All right? So, because if they're moving, then they generate magnetic fields, and the magnetic fields affect the forces on each other. Now, it turns out that the directionality is totally different than just a straight either repulsive or attractive force like we saw with Coulomb's law. The directionality is always three-dimensional. It's always perpendicular to the plane of motion, which is something we won't cover in this class, but that's kind of the idea, the story behind is such a phrase as complicated way. And it's just because of the nature of this and this idea of something mathematically called the cross product, okay? So there is a force due to the motion of the charged particles that we call the magnetic force, all right? So notice that there's quite a bit of different background here. We're not going to give you one easy formula for magnetic force. There's no Coulomb's law equivalent of magnetic force. The reason for that is, first of all, magnetic forces don't exist unless you have moving charges, all right? Whereas charge is an intrinsic property of particles, magnetism is not at all an intrinsic property. Magnetism is just a result of charges moving, okay? I can't stress that enough. Every single magnetic field that exists, from the lodestones to your fridge magnets to the magnetic fields of incredibly exotic stars like neutron stars, every single one of those magnetic fields is created by a moving charge, okay? Every one. And specifically an accelerating charge, because it's not enough to move in a straight line. All right, and so that's the big behind-the-scenes story, okay? And that's why you make the presentation of magnetism may seem a little bit different than that of electricity, okay? So to understand magnetism, it's important to understand the magnetic pole. So magnetic forces between a pair of magnets, there's a force of attraction or repulsion between the pair of magnets depending on which end of the magnet is held near the other. You've probably played with magnets and noticed this. Behavior is similar to electrical forces, right? Opposites attract, like poles repel, all right? And the strength of interaction depends on the distance between the two magnets, okay? So magnetic poles, this gives rise to magnetic forces. There are 2 types of interaction: north poles, which are north-seeking poles, and south poles, which are south-seeking poles, all right? The rule for magnetic forces between magnetic poles: like poles repel, opposite poles attract, all right? So in all magnets, they can't have one pole without the other. It is impossible. No single pole is known to exist. Simple bar magnets, poles at two ends. Horseshoe magnets, bent U-shaped, but then still poles at both ends. It's just that the poles now are kind of, well, bent into a U-shape. Okay? So, you're probably thinking, well, wait, isn't this the simple equivalent of Coulomb's law? I mean, we've got like repel and opposite attract. We've got an idea that the distance between them is, depends on the distance, and it weakens with the greater distance. But notice, no easy formula. And first of all, the distance doesn't even weaken with the square, so there's no inverse square relationship. Why? Well, probably best illustrated by this statement right here. No single pole is known to exist. That is reiterating what I said before, that magnetism is not an intrinsic property of particles. There's no magnetic particles, okay? If they exist, we just haven't discovered them, but they may not exist. They probably don't exist, all right? And certainly nowhere, nothing in our current understanding of physics suggests that they do. Instead, magnetism is only created by moving charged particles. Charge being, of course, an intrinsic property of matter, okay? So, but then you're like, wait, but these bar magnets, I mean, this is matter, and it's a magnet after all. So isn't that contradicting the idea that, I mean, well, sure, maybe, it has to come in sets of poles, but, a north and a south, but, it still, isn't it possessed by the bar magnet? No. And the fact that there is no single pole is really illustrating the idea that it is not possessed by a particle, because we have to zoom in and imagine the individual atoms, obviously much smaller than the dots I'm drawing, but the individual atoms that would make up this bar magnet. Well, within them you have electrons. Those electrons are in motion. If all those motions are aligned, then the overall effect is the creation of a pole within that macroscopic object, the bar magnet. Okay? But that's because of the alignment of the electron orbits or electron cloud motion within every individual atom. Okay? And even if every atom isn't aligned, then there's these things called domains. We'll talk about them in a minute, where you have pockets of aligned electrons in individual atoms. But the important thing, or in a metal, maybe it's kind of a sea of electrons that are moving, because of course the electrons aren't really bound to the nuclei in a metal. But regardless, the idea is that there is motion occurring at the atomic scale or just beyond the atomic scale that is actually creating the magnetic field. And since it's creating the magnetic field, that's why there's a north and a south. Okay? And we'll kind of get into that later, but that's the idea, is that the motion of the charges is creating the field. The field then has to, think field lines of Coulomb's law. That field has to go somewhere, and the very nature of the field that's created by the moving charges makes the north and the south pole. It's not intrinsic. It's created by moving charges. All right, so a weak and strong magnet repel each other. The greater repelling force is by, well, both the same. Think Newton's third law. All right, so magnetic fields, right? Mentioned, this idea that the magnetic fields are created by moving charges. Well, what are they? Well, the regions of magnetic influence surrounding magnetic poles. Their shape is revealed by lines that spread from one pole to the other. By convention, the direction is from the North Pole to the South Pole, all right, which is produced by the motions of electrical charges in atoms, okay? So here's, there's a good statement right there, because, they can't have poles without moving charges, okay? So but then, just like by convention, electric fields, and this is a good one, it's so easy to forget. Which way do electric fields point? Electric fields point in the direction that a positive charge would experience a force. So that means all electric fields point towards negative charges and point away from positive charges, okay? That's the convention. Similar convention, all magnetic fields point in the direction from the North Pole to the South Pole, okay? So, in other words, the magnetic fields are as if you were to put a bar magnet, and the bar magnet would align itself with the north pointing in the direction of the magnetic field, okay? So it's like north is to magnetic fields as positive charges are to electric fields, okay? All right, here's a popular picture with the idea of putting iron filings and having those iron filings show the direction of the magnetic field. All right, and so the direction then of the magnetic field would be something like this. Okay, see, these are the field lines, all pointing to the south. All right, you can imagine some coming around this way. Okay, get the idea? Okay, the field lines spread out further away from the bar magnet you go because the effect of the magnetic field weakens with distance. All right, so the strength is indicated by the closeness of the lines. Right near the poles, the lines are closely packed together. The lines aren't perfect here because, of course, the iron filings have their own inertia, and they can experience non-conservative forces like friction, and so. But they're still a good illustration, if a rough one, of the field lines. The lines close together, strong magnetic field, and the further apart, that's a weak magnetic field. So over here is a weak magnetic field. In fact, the iron filings become they're not very well aligned with the field because there's actually not enough force to actually move them around easily. All right. So where do they come from? Right? I mentioned this a couple times, but we have a very, very good picture here. They come from electron spin. Okay. All right. And revolution. Okay. And so they come from the fact that the electrons are spinning, just like Earth is spinning and has a 24-hour spin around its own axis. And they come from the fact that the electron is orbiting, which we call the revolution. That's the revolution around the atomic nucleus. That's the motion that leads to magnetic fields in solids. Now, you can have magnetic fields that exist in gases that are maybe due to the actual motion of the atoms rather than the motion of the electrons within the atom. But regardless, it always comes down to moving charge. And in that case, the atom would have to be ionized because if the atom is neutral, right? If the atom is not an ion, if there are just as many electrons as protons, then the bulk movement, the full movement of the atom will not create a magnetic field because it's a neutral particle. And then just like here, then the only magnetic field is going to be that created within the atom. All right. But inside atoms, there's always a magnetic field created because that electron is always accelerating. Because remember, circular motion is a form of acceleration. And acceleration of any charged particle, in this case the electron inside the atom, creates a magnetic field. One of the most beautiful ideas in physics. Okay? All right, so the electron spin, even though you might think that being the smaller motion, is the much bigger contributor due to just the parameters of the way the actual spin of the electron as opposed to its orbit, how they differ. So creates a very strong magnetic field. The north points in this direction. In fact, the north points in a direction that you can figure out with your right hand. I won't ask you on this, but ask you on this on an exam or require you to know this, but I think it's fascinating. You curl your fingers of your right hand and your thumb points in the direction of the magnetic field. All right? And that would be, you curl your fingers in the direction that a negative charge would be moving if you use your right hand, and then your thumb points in the direction of the magnetic field. All right? Well, specifically, it points towards the north. Okay? See that? Do it yourself, right? Curl your fingers in the direction of this, right, like that, and you'll see your thumb naturally points in the north direction towards the north pole of the magnetic field. And so look at this. This is a magnet, right? Doesn't look like a magnet because it's just an empty space, but it is a magnet, right? And that's the idea. Magnets often exist as abstract ideas in empty space. We create what's called a magnetic dipole, right? We just kind of create a magnet that's sitting there, right? That, of course, the field lines continue off into space, but in effect, we've created this sort of virtual bar magnet that exists just due to the spinning motion of the electron. Okay? All right, so the source of all magnetism is, okay, I made a big deal about this, right? Electrons rotating in an atomic nucleus or electrons spinning about an internal axis, okay? It's just electron motion, absolutely, unequivocally. All right, so where magnetic field lines are more dense, the field is, got it, stronger, okay? So now, more about magnets and solids. I mentioned the idea of domains. These are pockets of aligned atoms, all right? So magnetic domains, magnetized clusters of aligned magnetic atoms. Permanent magnets are made by placing a piece of iron or similar magnetic material. Some materials are better for others, and you can get, like man-made ones that are better than pure iron. Think neodymium, right? Neodymium is a naturally occurring element that is very good for creating strong magnetic domains. So in a strong magnetic field, stroking the material with a magnet to align the domains. The idea of actually, and you can do this if you have one of these magnetizers, you want to magnetize your screwdrivers in your tool set, you actually have a magnetizer, you basically rub the steel against this magnetizer, and it will, for a while, sometimes weeks or days, even months, will magnetize that screwdriver. But you have to actually put in that physical motion, because essentially what you're doing is you're heating it up, and you're putting in that mechanical energy, thus allowing work to be done on the charged particles, and due to the presence by doing that in a magnetic field, because essentially the magnetizer is a permanent magnet. Doing that inside that magnetic field means you're left with a fairly stable magnetic field in your steel screwdriver. Okay, but when I say fairly stable, that's because it really won't last forever. It won't last as long as other materials like iron or neodymium. All right. So the difference between permanent magnets and temporary magnets. So a permanent magnet, the alignment of the domains remain once the external magnetic field is removed. And there's definitely, like I said, there's a gray area there. And in temporary magnets, the alignment of the domains return to random arrangement once the external magnetic field is removed. A great example of that is, a paperclip. You hold the paperclip to a bar magnet, and then that paperclip then can pick up a next paperclip, because that paperclip now has become a magnet. It has aligned up its domains with that of the permanent bar magnet. But once it's removed, it doesn't stay magnetized. Okay. And now you could help it stay magnetized if you rubbed it on the magnet, especially if the magnet has certain properties. But at the end of the day, it still is a temporary magnet. Okay. Now that said, in all reality, if you think of solids, even if they're lodestones, if they're lead, if they're neodymium, even then there's no such thing as a truly permanent magnet, because just natural processes of entropy are going to eventually lead to those domains becoming misaligned. But some of them will remain for a long, long time and thus seem pretty permanent. All right. So back to the idea that there's no such thing as a monopole, which is there's no such thing as getting a south pole or a north pole by itself. You can get unmagnetized iron. You can magnetize it. See the idea here that all these little domains, and domains are made up of millions of individual atoms, but we can kind of think of them almost as playing the role of having one lined up electron within an atom. So here there all these atoms are just randomly aligned. This is the natural state. Once you start to magnetize it, you can see they start to get aligned. If you continue to put energy into the system and then create a strongly magnetized piece of iron, then you have almost perfect alignment between the domains. They're all pointing in the same direction. In this case, all these little magnetic field lines pointing in the north direction. If you then cut that magnet in half, what you're going to get is two smaller magnets. Okay, you're not just going to get a south pole and a north pole by itself, not at all. But of course, that's the case. That makes sense because this is happening at this microscopic scale of 10 to the let's see, 10 to the negative 10, maybe 10 to the negative 9 meters. Because if the individual atoms are 10 to the negative 10, then we're talking a very, very small scale, nanometers or smaller. Okay, so connection between electricity and magnetism. Magnetic fields forms a pattern of concentric circles around a current carrying wire. When the current reverses direction, the direction of the field lines reverses. Okay, so a steady current carrying wire creates a steady magnetic field, and it creates a magnetic field in circles. Okay, and we can see that the direction of the magnetic field, if we do it like this, then that would be pointing towards the south. Okay, so that you have a bunch of north poles on all these little compasses that are being kind of aligned on this piece of paper here. Okay. And so and the concentric circles, they're just like any magnetic field line, they represent strength. So you have tighter concentric circles immediately around the wire, and then they start to become more widely spaced out the further you go, when the influences of the wire that created the magnetic field become less pronounced. Okay, so here's another picture of it. This is a current carrying wire. Okay, why does a current carrying wire create a magnetic field? Because any moving charge creates a magnetic field. Now here's the thing. Okay, now I made a big deal about accelerating charge, and actually accelerating charge is super important for creating light, which is then basically a chain reaction of magnetic fields creating electric fields creating magnetic fields, and so on. And we'll talk about that in the next chapter. It's called Faraday's law of electromagnetic induction. But here you actually can create a magnetic field with a constant current. So you can have the current be constant and still have a magnetic field. It's just that the magnetic field itself will be constant, and that's the end of the story. All right. On the other hand, if the wire is being, if this is part of a circuit and it's being switched on or switched off for that immediate second as the charge is building up in your circuit, there is a moment where the current is non-steady, and when you switch it off or unplug it, there's another moment where the current would be unsteady in the circuit. And at those moments, there's still a magnetic field, but it's a changing magnetic field. And you'll see in the next chapter that's a big deal. Okay. All right, so magnetic field intensity increases the numbers of loops. The loops increase in a current carrying coil, which is a temporary magnet. So when you have a single wire, yeah, you can see the concentric circles. If you have a loop like this, you can still see the concentric circles, and you can actually see a region in between where you start to have a nice uniform magnetic field. If you put a lot of concentric circles, almost like the binding on a notebook, you can have a very, very well-defined region inside of those loops where the magnetic field is functionally basically uniform. And then what happens is the magnetic field cancels out outside of the loops. So then you have a region of very weak magnetic field immediately outside the loops. And so that's what's called a solenoid. Okay. Also just called a magnetic coil. All right. So electromagnets, an iron ball is placed in a current carrying coil. Most powerful electromagnets employs superconducting coils instead of just normal wire, which eliminates that core. Applications: control charged particle beams and high energy accelerators, lift automobiles and other iron objects, levitate and propel high-speed trains. Right, so lots of interesting applications. An electromagnet can be made stronger by, what do you think? Right, both increasing the number of turns in the wire and increasing the coil. The stronger the current, the stronger the magnetic field. All right. So electromagnets, well, a current carrying coil of wire is always an electromagnet. Every current carrying wire creates a magnetic field. Sometimes that's undesirable. In a lot of electronics, you have to deal with that magnetic field that's being created. You have to realize that it's going to affect your circuit. It can mess with your results if you're trying to do a careful experiment. Then just like the current carrying wires in the walls of your lab can interfere with your experiment because they're creating magnetic fields all the time. There's all these ambient magnetic fields because of all the current carrying wires that are surrounded by us. If you happen to live near high voltage, power lines and overhead, that can create very pronounced magnetic fields in your home all the time. And that's why people talk about the health effects of living near those high voltage wires. That's because of that magnetic field that's always just there. All right, because it's an electromagnet. Okay, but sometimes you want to make an electromagnet to lift something. So the strength of electromagnets is increased by increasing the current through the coil and increasing the number of turns in the coil. All right. Also having a piece of iron within the core. So essentially, like if you imagine like taking this one here and putting this as an iron core, that really helps with the strength because it'll kind of like it boosts the alignment of the magnetic field inside the coil. Magnetic domains in the iron core are induced into alignment, adding to the field. So this is more about the applications. I'll let you read this on your own. Okay. So in summary, we have that moving charges in a magnetic field experience. Oh, this other side of the coin. So now imagine that a magnetic field. We know one way to create it is through current. All right. So you have current running through a wire and you create a magnetic field. Also, we know that you can create magnetic fields inside of individual atoms because the motions of electrons inside individual atoms always create magnetic fields. Now, here's the interesting thing. What if you then have another charge, like an electron, pass by? Is it going to notice that magnetic field? Absolutely. And now we're starting to see kind of the whole story here, although it will come into more full focus in the next chapter. Any moving charge will notice that magnetic field. And in fact, even a static charge will notice that magnetic field, okay? So what's going to happen is, actually let me rephrase that. Any moving charge, a charge at rest will not experience a magnetic field, all right? But any moving charge will have a force acting on it when it's moving by and there's a magnetic field through the region to which it's moving. Now, the real story behind that is because the moving charge creates its own magnetic field, so it's actually an interaction between magnetic fields, but it looks like it's an interaction between a magnetic field and the charge because we see the charge being acted on by the magnetic field. All right, so it's kind of like it's this idea that there's an appearance of a force, but in reality, the force is all coming from the moving charges. Okay. So the greatest force are particle movement in the direction perpendicular to the magnetic field. All right. The least force is when a particle is moving parallel to the magnetic field. All right. Or basically less force is anything non-perpendicular, and then no force is parallel. So if I have a magnetic field that points this way, I'll use B for magnetic field, and then I have the velocity of a charge like an electron that points this way, then this would be 90 degrees, and the electron would actually experience a large force from the magnetic field. On the other hand, if the electron was moving in this direction, then it would experience no force from the magnetic field. Okay? All right, so here's an illustration of the idea. This is supposed to be three-dimensional in terms of the magnetic field, the beam, and the force. Okay? So that's where it inherently is kind of complex because it is a three-dimensional idea, right? The beam, you can imagine it moving out of the page. The magnetic field is pointing to your left, and then the force is pointing up, okay? So this is an example of the force that would be experienced on an electron, okay? All right, so the reason an electron moving in a magnetic field doesn't pick up speed is because the magnetic force can never do work on the charge. It can only change its direction. So it exerts a force on it, but that force is doing zero work by definition because work can only be done if the force is parallel to the displacement. But here the force is always perpendicular to the displacement. Magnetic fields do no work. They can change direction, but they cannot slow down nor speed up electrons or any charged particles. All right? That very nature of being perpendicular is so interesting in the way it ties in with energy conservation and the whole ideas of physical work. All right. So the magnetic force on a moving charged particle can change the particles. Okay. Think about it. If you can't speed it up or slow it down, it's not going to be speed, is it? Just direction. Magnetic fields can only change direction. They can't change speed of charged particles. Okay. So one manifestation of this force that is exerted on moving charges is visible on wires, because wires are composed, if there's a current running through the wire, there's a bunch of moving charges in that wire. Therefore, the wire itself will actually bend or buckle or be lifted in a direction that is consistent with the force from the magnetic field. So the current of charged particles moving through a magnetic field experiences a deflection force. The direction is perpendicular to both the magnetic field lines and the current, all right? So the idea of being perpendicular to two things, that's such the mathematical reality of magnetic forces. Again, it's called the cross product in official magnetic, or official mathematical terminology. So this deflection force is strongest when the current is perpendicular to the magnetic field. If it's parallel, there's no force at all. All right, so electric meters detect electrical current, and they do it by basically having a compass inside of a coil of wire, and the deflection of that compass will tell you how strong the current is. All right, that creates what's called an ammeter, or here it's called a galvanometer, because it's based on that principle. It measures amps, hence also the term being called an amp meter. You can also create a voltmeter based on the same principle. All right. Electrical motors are based on this principle, because when you run current through the wire, then the current experiences a force. Then if you have that force, or that have the current change directions every half rotation, then you can create a steady spinning motion. Beautiful, isn't it? That's how every electric motor works. All right. So a motor and a generator they're actually the same thing. They just work backwards. In the one case, you put in the current then has a force impeded on it or acted on it by the magnet, okay? And that then, causes rotation. On the other hand, you cause the rotation through some other mechanical force like falling water or rising steam that spins the coil through the permanent magnet, thus creating the charge. So you either supply the charge or you supply the mechanical rotation, and then you either get the mechanical rotation or the charge. And that's what generators and motors are. And wow, talk about a big idea that is so applicable to our lives, because every single power plant is based on this principle, whether it's a nuclear power plant, a hydroelectric power plant, or a wind turbine. All right. Okay. Well, I hope these ideas are interesting, and I look forward to talking about them later. More. Thank you so much for watching this video.